Right, good morning. We're going to finish this short lecture today and start with the methodology of hard operational research, I guess. We were talking about modeling and we discussed what models meant. Lütfen. And we have discussed the attributes of good models. The first one is that it should be simple enough, but also realistic enough to be suitable for use as a means of communication, as a tool for thinking. Next, on this slide, I think this is one of the most important type of advice I try to give students, especially next year when you take up the systems design courses. When you embark on your project, most student teams often have to construct mathematical models, and they do not really know how to go about it because they would like first to wait until all the facts are known, all the data is collected, and then they think that they will construct the model from scratch just as in its final form, and then they will use it. It doesn't work out like that, okay? When you're constructing mathematical models, you cannot come up with the latest version of the model in the beginning. You have to start small, then add and refine, okay? What we mean by this is that start with a small model, even if it is not sufficiently realistic. Now, a model, of course, is a construct, as we have explained in the definitions part of the lecture, that illustrates the way you view reality. It's your personal view of reality, the model. And you construct it for the purpose of controlling or changing or engineering some part of that reality. You're going to make an intervention in the reality and change the way it is in some way. Then, of course, you have an understanding of what your model will be useful for, what sort of a decision that you will take. It will support what sort of a decision that you will take in the future. So you have a conception of this model. Just construct that essential part of the model. It doesn't matter whether it is small or not realistic. Make sure you immediately solve and test it numerically. This is the most important thing that you should remember about model construction. Don't wait until you refine all the features of the model, obtain all the realistic data, make all the calibrations, and then expect to get a solution. Get the solution at the earliest possible time, even when you don't have real data. Just make the data up. Just leave out the many complications. Keep it simple and immediately get a solution. Look at the solution and think about it. Does it make sense? Does the solution tell you anything useful? Okay? In this way, you will be the master of your model. You will be able to construct the model as you need it. If data is not yet ready, use approximate data or use guesstimates. Guesstimate is just an informal estimate. This will show if the model makes sense, if it helps you to understand the problem situation. Only after you get an output from a computer, obviously your models will be sold on computers, and looking at that output, will you be able to appreciate whether your model is good for anything or is just useless. As you discover the shortcomings of your model, obviously it will not be realistic enough if you keep it very, very simple. Then, of course, you have to refine it. You do this either by making it richer, by enriching the model, that is adding new features and components. Usually, this works out as adding new decision variables, new constraints, and things like that. New relations are represented in your model. Or by reformulation. You can see from the results, the numerical results of your first experimental runs, that the model doesn't make much sense. So you have to reformulate it. You have to formulate it from another point of view, maybe change the objective function, maybe change the way you model the relationships, etc. So essentially, it may be necessary to construct a new model. So this slide is really, I think, important for you to understand and remember and keep in mind all the time in your profession when you are dealing with modeling. A good model has several attributes. It should be adaptive. Adaptive, we understand what adaptation means now. What does it mean, adaptation? Yes, learning under new conditions or accepting the new conditions and making modifications as necessary. In the case of models, of course, the data you obtain later on during the course of your project, the research project, your inquiry, may indicate new features and new facts can be revealed, etc. So you should be able to adapt your model to address these new situations. In this way, the model should be adaptive. It should be robust. Well, robustness is a little bit more difficult to achieve because robustness, you understand what we mean by robust. Huh? In optimization theory, for example, you obtain an optimal solution from your model. We say that the solution is robust. When can you say that your solution is robust? When it is not sensitive to small changes in the what? In the input data, right? In the input data. For example, you get in linear programming, you obtain a basic feasible solution which is optimal, okay? So the optimal basis has been determined, but you are not sure about your data, and one of the values on the right-hand side column or somewhere in the matrix, A matrix, etc., if you make a little change in one of those values, then maybe the basic feasible solution will have to be changed. The optimal will move, the optimum now will lie in another basic feasible solution. In this sort of situation, the original solution you have obtained is very sensitive to changes in the input data. This is how we try to, this is why we conduct a sensitivity analysis to see whether the solutions we compute are robust or not. If the solution does not change, even when the data changes a little bit, then we say that the solution is robust. Robust means healthy and strong, robust. So a robust model, of course, is a model which will not have to be modified even when external conditions change, but this is difficult. It should obviously be appropriate, so these underlined attributes are the attributes of a good model, appropriate to the problem situation. For example, it should allow solution within the time frame needed. I mean, if you construct a model that you cannot solve easily when you need the solution in the next half hour for online applications, for example, then it's not an appropriate model. Obviously, it should be relevant and appropriate for decision making. That is, without extensive need to process model outputs. I mean, if your model is putting out loads of data, which at the first sight is useless and meaningless, but needs further processing in order to make it useful for decision making, etc. So it's not a very good model. Your model should be better than that. Obviously, in some cases, you have to provide interfaces that take the output of the model, process it, and put it into usable form, etc. So all of these features are, I think, easy to understand. Aided by diagrams. Now, this is important. This is, of course, not an attribute of a good model, but a way to construct a good model. In order to construct a good model, it is useful first to start with diagrams. Usually these are influence diagrams. An influence diagram is a diagram, as we shall see examples later on, and I'll ask you to construct these in examinations and things like that, in term projects. An influence diagram is a diagram, it's like a flow chart. I don't know if you are having to write computer programs anymore. Usually these days, computer programs are just ready-made packages. But when I was working as a computer engineer after graduation, I used to write many codes in Fortran, COBOL, and several other languages like programming language 1, etc. And when you write a complicated code, a long program, it's possible to make several mistakes, and it takes time to clear away those mistakes. A better way is to first provide the flow chart of the program. There were templates provided by the IBM Corporation, and they were difficult to obtain. And when you obtain those templates, you could draw nice little circles, cylinders, triangles, etc., into which you wrote the codes first in the form of a flow chart. And then from the flow chart, looking at the flow chart, you could do the coding in an easier way, and it would without many mistakes. It is similar. An influence diagram is similar to a flow chart that you first construct before programming. This is something you first construct before you write your model, influence diagram. So these models should be used for going back to rich pictures and mind maps for revision of both these and the model. Okay, so you use your model interactively with the graphical constructs you should have done before, like rich pictures. A rich picture, for example, is the first thing that you should think of when you embark on a new project. I mean, it will be a good idea to do these in the systems design courses next year. But even when you start your professional careers in companies or in workplaces, and you start to inquire into a new problem situation as part of your responsibilities as an industrial engineer, it is a very clever idea to start with a rich picture, rich pictures, mind maps, etc. Once you construct these rich pictures, it's not just for showing it to somebody else and then keeping it in a file. It is useful for yourself, for you. You go on from the rich picture to formulation and to constructing models, etc. You construct your models, obtain some preliminary solutions from that, and this provides new learning about the problem situation, which then asks you perhaps to go back to the rich picture, make modifications on it, come back to the model, etc. So this sort of interactive comings and goings between these parts of your inquiry are very important in our profession. An influence diagram, for example, can be constructed using these elements. Now, when you construct diagrams, some diagrams have there are some kinds of diagrams known under specific names. For example, if you talk about an influence diagram, then there are rules that you have to observe when you construct those diagrams. It's like a syntax or the language of the diagram. Unfortunately, most students are very careless about diagrams. They put all sorts of boxes on the diagram and write all sorts of items into the boxes. I mean, if you have a box, for example, like a rectangle over there, then all the boxes of this shape should include the same type of content. Some types of content will only appear in circles, for example, and not in rectangles. You should be careful about these things. So an influence diagram has these shapes that are rectangles in which you write variables which are control inputs, which means your decision variables probably, and decision rules, etc., can be written in those rectangular boxes. And then in circles, we write the system variables, which are, what are the system variables? Sorry, in the rectangle, we don't write the decision variables. We write the inputs, okay? Input value, inputs to the narrow system of interest for which we are trying to construct a model. Here in these, you write the variables. It says rates and levels. What do they mean? What are they? We have seen these concepts before, but under different terminology maybe. What is a rate? What is a level? Yes, a level is a stock. A rate is a flow, all right? It's like x and dx to dt. Dx to dt is the rate, x is the level. So all these variables, for example, should be represented in circles. The cloud shape at the top over there are the input data, the cloud, parameters, constraints, etc. They are external to the model, which are external to the model. And the output is represented in an ellipse, the output. The output is what you try to obtain from the model. The influence between these shapes is indicated by arrows, as you can see. An arrow going A to B says that if, for example, the arrow connects two circles, then it means that the variables in the circle A will change the values of the variables in the circle B. And in this way, the influences are indicated. So rates, flows are process element, levels are stocks, structural elements. So these are the elements of an influence diagram. Here is an example of an influence diagram from the textbook. It's not a very good example. We shall have more concrete and better or useful examples later on. As you can see here, the output is at the top right-hand side. It says shipments. So this is a production inventory system. So you make decisions about how much to produce and how much put it into inventory, how much to send directly, etc. As a result of which you will have to make some shipments. It is better to, influence diagrams can be constructed in this way at the very beginning, where you write words like shipments instead of variables and symbols. So, for example, finished goods stocks, it says in a circle over there. So that's, it could be represented by X sub t, for example, which represents the amount of inventory, if there's only one type of inventory, at time t. But it is possible to start an influence model like this without using algebra. But then, to make it useful, just before you use it to construct a model, it is best to put algebraic expressions in all these shapes. It's much better in that way. So this is not a very, very nice example, but you can see, for example, the demand is external. At the top over there, it's in a cloud. So demand data is determined, it's data, it's in a cloud, it's data. So once we know that, for example, we can put the demand into the order book. Then the demand data will also tell us what the order pattern is. And then maybe we shall obtain a forecast from this data, a demand forecast, etc. So you can see all the steps. There are other parameters, supplier lead time. For example, you need some supplies coming from some other company in order for its raw materials, as you can see. There's a lead time associated with supply. You cannot obtain the raw materials just without any lead time. So that sort of data has to be fed into the model from the outside, etc. So this is a first example, although not a very, very good example of an influence diagram. There are other types of diagrams that are useful in constructing models. These are flow charts, spray diagrams, etc. Flow charts are used to show logical or temporal flows, such as material flows, information flows, decision flows, etc. But you shouldn't, for example, construct a flow chart in which some boxes indicate materials and other boxes indicate information. They should all be of the same type. I mean, you don't mix a material flow chart with a decision flow chart. You have to separate them and draw them independently. Spray diagrams, you are familiar with these. These are also called fishbone diagrams. Maybe this is the term you use more often. These are useful to map cause and effect relationships, spray diagrams. For example, do we have examples? Yeah, I think we have some examples. This is an example of a spray diagram. As you can see, it's a cause and effect. It tries to establish a cause and effect relationship. What is the effect? The effect is at the end of the arrow, the horizontal arrow at the right-hand side. It's customer dissatisfaction. In this company, they have observed that the customers were not satisfied with the services of the company. So what are the likely causes of this dissatisfaction? The primary causes, there are 1, 2, 3, 4 primary causes represented by the 4 arrows ending on the horizontal arrow. One is design, the other is customer error, the other is cost. The 3 actually, this is just a representation, the main cause. And then there are other arrows feeding on the secondary or the tertiary arrows, which are the secondary, tertiary, or causes of the second degree, third degree, fourth degree, etc. So these are spray diagrams. These are useful to understand cause and what causes customer dissatisfaction, for example. Precedence charts are useful in project management. Precedence charts are the charts like CPM and PERT charts. You are familiar with project scheduling using CPM, right? Do they teach you in these in the OR courses? Öğretiyorlar değil mi? CPM. Okay, well, you will. These are simple rules. For example, a CPM diagram. These are used mostly in the construction industry, but now they can be used anywhere in any project. But initially, they were formulated or designed for construction projects. I mean, you cannot put the roof before you put up the walls, for example. So there's a precedence between the activities of roofing and construction of the walls. So these are precedent charts. The general rule for all such diagrams is that the components of the same category, for example, circles, squares, etc., should only show entities of the same category. This looks obvious. Well, I am sure that you will all make the mistake of not obeying this rule. I am sure about it. It always happens. Next year, you forget all these explanations, and when you start the system design course, it is as if you are starting from zero. All the knowledge and the way to proceed in the systems design courses next year are here in this course. Huh? You should learn to connect one course to the other. Huh? I give this advice all the time. It doesn't work out very well, unfortunately. Okay. So this is a flow chart of a power system. Huh? It indicates the flow of water. There are reservoirs and power stations, etc. So you can reservoir station. This is the legend. Huh? You have to provide a legend. Tributary means a river which feeds on a larger river. Huh? Kol, yani nehrin kolları. Canal, bypass junction, etc. So, and here's a decision flow chart. Customer orders come in, X. Then you have to decide whether it's a large order or a small order. Then you have a rule. Is X greater than or equal to L? L is some point that you have determined previously. If the order is greater than L, then you schedule a special production run of size X. So a special batch production is performed to produce or to manufacture for this order, and then it is shipped to the customers. But if the stock, if the order size is less than L, then maybe it's a small order. You can satisfy it from your inventory from your stocks. So you check whether there is enough inventory to satisfy this order. If the answer is yes, then you take X from stock and ship it to the customer. If there is not sufficient inventory, then you have to replenish your stocks, etc. So this sort of decision flow chart is also useful in understanding. These are not for modeling. Huh? This doesn't help you for your model construction. The diagrams for model construction are the influence diagrams. Don't confuse them. This is for understanding. This is also a preliminary to modeling, but a few steps back in time. The step which is closest to modeling is the influence diagram. This comes before that. This comes when you are trying to understand the problem situation. So there are several such diagramming techniques, diagramming tools that you have to understand and use all the time. You have to use these all the time. Our students submit reports on some project they do, for example, summer projects it could be, or some term project, whatever, and even master thesis and PhD thesis. In the PhD you don't have much difficulties, but even in writing a master thesis, students tend to write everything in words without using that. But an engineer, true engineers, not industrial engineers, use diagrams all the time. They depend on diagrams. They cannot do anything without diagrams. Unfortunately, in our department, we are not able to obtain this affinity or this ability to use diagrams efficiently. You have to make use of diagrams. Diagrams are the primary tools of engineering. Right? So that completes this short lecture. This one is a longer lecture. This is the substantial lecture. This is about how you conduct operational research. What's the methodology of operational research when you are doing hard inquiry? This is the traditional operational research that you are learning. Hard OR. Well, the content of this lecture is as follows. We first classify problem situations. This is very, very conceptually useful classification, as we shall see, as functionalist, interpretive, and emancipatory problem situations. Problem situations that call for a type of inquiry. A problem situation has some properties, attributes, which makes it necessary to address this situation using a different perspective. These differences in perspective are three: functionalist, interpretive, and emancipatory. Then we talk about hard OR and hard systems thinking and look at the methodology of hard OR or hard systems thinking in three. There are three steps in conducting an OR methodology. The first one is formulation. The second is modeling. And the third step is implementation. All OR projects follow this sort of phases, the three phases. And then we are going to look at an example project in detail, the LOD project. And I have determined a term project for you. Our assistants and other professors, I have asked them to find a suitable term project for you. But then I found it myself yesterday. So I'll be giving you, it's an old project that I used several years ago. Don't ask me how many years ago, you will be surprised. But it is a very, very nice project. So you will be asked to conduct a similar project. When we initiated this systems thinking course, in the first few years, we tried to have our students do a project, work on a soft project, a soft OR project. But the last year and the year before that, we changed our minds and we made it a hard project. A hard OR project is the project that you are used to normally, which includes mathematical modeling. In soft projects, mathematical modeling may or may not be possible. The reason why we did this is because there's really no opportunity for you to learn how to conduct a project, and most importantly, how to report your work. Writing a project report. This is, I mean, our students are very, very poor and ill-equipped to write reports. The reports they submit is usually rubbish. The reports that you write are extremely important for your profession, for your advancement in your profession. If you learn how to write good reports, believe me, you will make a lot of money. This is absolutely true. So learning to write good reports, engineering reports, is essential for your professional careers. And I will ask you to write a good report in this project. The report is even more important than what you do in the project, because what you do in the project is simple. It's not a very complicated project. But going through these phases of formulation, modeling, implementation, in the formulation step, for example, being able to use and being able to demonstrate that you know how to use all those rich pictures, diagrams, flow charts, influence diagrams, etc. And then bringing all them together to construct a model and to plan the implementation of the recommendations you get from the model, and reporting and communicating these intelligently and usefully to somebody else. This will be an exercise, an opportunity for you to have an exercise on that. Okay, so this is our content. Let's look at some diagrams which may not be in your textbook, but they are useful diagrams. This diagram is from Jackson and Keyes. It's a classification of problem situations. You can see a map here. This is like a map. The borders of the map are shown in red letters. Inside the map, we have 1, 2, 3, 4 areas. It's as if the geography of all problem situations. Some problem situations fall in some area of this map and some in others. So as you can see, here we have hard OR. For example, some problem situations, therefore, lie in the world of problem situations where we understand them as hard OR problem situations. Now, how do we determine, how do we define hard OR? Well, there are two elements, two dimensions that define the type of problem situations. One is here. I called it systemicity. Now, we used to call it something else, but this is a better term, I think. Systemicity is the attribute of being a system, having the attributes of a system. And the other dimension is divergence of values and interests. Okay? So as you can see, hard OR falls under the headings of unitary divergence of values. What does it mean, unitary? Unitary value. Single, one. Unitary means one. So what should you understand from this? Unitary in terms of OR. There's a single objective, unitary objective, unitary values. There is a single interest. For example, the entire interest for you in the inquiry that you are conducting is to minimize costs. You are focused on a single unitary interest, minimization of costs, okay? In this sort of situation. And secondly, systemicity is not very strong, weak. I mean, you can ask me, what do you mean by a weak system? We didn't talk about systems being weak or strong. Huh? But, I mean, roughly you should be able to understand. Systemicity is very synonymous with complexity. So weak, the interconnections are not too many, all right? Uncertainty is not really very strong, etc. So it is like a simple system. I don't want to use the term simple system, but you can think as if hard OR deals with problem situations that serve unitary interests, and the system is relatively, let's say, simple. Okay. Then on the bottom here we have hard OR and systems thinking. So the attributes of systems thinking are more relevant here. They are also relevant in hard OR. I mean, hard OR uses systems thinking all the time, but systems thinking, how shall I say, in underlined and strengthened way is needed in when you deal with, even under unitary interest conditions. When systemicity is strong, you need to be more careful about systems thinking. Then you have another area which says pluralistic. Pluralistic obviously means there are a multitude of interests, not only a single interest, but many interests. So it is not, for example, easy to write one objective function and try to optimize it and obtain some recommendations for action, because there are more than one interest. In this sort of situation, usually soft OR and systems thinking is called for. What do we mean by soft OR? Well, it is not very easy to make these distinctions. I mean, soft OR also includes hard OR. Hard OR also includes soft OR. They overlap all the time, so it's not. But soft OR, in soft OR, you can still sometimes make use of mathematical models, but you should be more careful about how to use them. Then in the final part, you have interests which are conflicting. Under pluralistic interests, you can still observe, we can still have conflicts, but some of these conflicts are reconcilable. Somebody, there's a give and take, and they can meet at a point. The conflicting interests can reconcile, and barışabilirler with each other. In the conflicting case, these interests are irreconcilable. This area on the right-hand side is something we shall not address in this course. It is a new area. It's the most difficult area for OR. It's soft systems thinking. Emancipatory approaches, etc., are to be used in problem situations falling in that area. So this is a good first rough sketch of how problem situations separate each other into regions like these. Now, I have included here some material which is not in the book. These are concepts which we have formulated during the course of this systems thinking course through the years, in order to understand what we mean by complexity and how it should be addressed using different approaches. We have to understand complexity in operational terms. It is useful to distinguish between ways that complexity acts in the three dimensions of complexity. You will not find these terms in the book or in the literature, dimensions of complexity, but it makes sense. Complexity, we have a fair understanding of complexity from our readings, from the last lecture, etc. But now we are trying to make all those concepts more operational. So it can be understood in three dimensions. Complexity has, it's as if saying that complexity has three dimensions. One is the technical, the second one is the probabilistic, and the third is purposive. Technical complexity is the easiest to understand. For example, in the pickup and delivery vehicle scheduling problem we discussed. cargo problem. There's a huge number of courses of action. You remember there were 20 points and the number of possible routes was astronomical, etc. This sort of complexity is called, you can call it technical complexity. In order to compute an optimal route, for example, to visit those 20 points of pickup and delivery points, then you may have to solve an optimization problem which is computationally complex. You remember computational complexity I discussed last? I said some problems are NP hard, and you need an exponential time of obtaining a solution as a function of the problem size, which takes billions of years for a computer to work on, even in 20 points. So this sort of complexity is technical. Then you have probabilistic complexity. Another way of calling it is uncertainty. For example, in the same problem situation, demands and traffic congestion are not known in advance. You would like to route your vehicles in some way, but of course you don't know whether on a bridge, for example, there's an accident and the traffic has been stopped there. So this sort of knowledge is not available. So if this uncertainty is high, then complexity also increases in that way. Finally, purposive complexity means diversity of interests and values. It is you remember the horizontal axis on the Jackson-Keyes diagram. It's this component of complexity. For example, in screening for breast cancer problem situation, there will be conflicting objectives among stakeholders. For example, the women's groups who are worried about, who are concerned with cancer, breast cancer, for example, will want sufficient number of mammography machines installed and an efficient screening of the entire population in that area to go through this screening in order to be able to diagnose, for early diagnose, to be possible. But the Minister of Health, for example, who is paying for the project, has other priorities. I mean, screening for breast cancer may not be the #1 health problem in the country. There may be more other. So this sort of complexity is called purposive complexity. Greenhouse gases causing global warming, as you know, is a very, very serious problem which is confronting all of us, all humanity. It has a high degree of complexity in all three dimensions, this greenhouse gases. It's technically complex, it is probabilistically complex because you don't know what's going to happen in the future, and also extremely complex in the purposive dimension as well. So these three dimensions are useful to understand. Now, this is a very nice diagram from the textbook, which I have modified just a little bit. It is a useful diagram, but it is also misleading. So let's please pay some attention to this. I will try to explain this because it causes confusion. Now, you can see here three dimensions that I mentioned. On the horizontal dimension, the vertical dimension is probabilistic complexity. The horizontal line is purposive complexity, and here we have technical complexity in 3 dimensions. So the space, the 3-dimensional space here is like the projection of this 3-dimensional space into 2 dimensions was this space. Now we take this space and extend it into 3 dimensions. So the entire space of problem situations is this volume, or the positive orthant, where all the variables are positive, of the 3-dimensional Euclidean space in geometry. So this is the space of problem situations. As you can see, as we approach the origin, there's an origin, then complexity decreases in all dimensions. Technical complexity decreases, uncertainty decreases, and also Purposive complexity means as we move to the origin from the right-hand side, the number of different possible objective functions is decreasing. Right? If you move along the horizontal horizontal axis to the right-hand side, the number of conflicting objectives interests are increasing. It's as if you are trying to model the situation using mathematics, the number of objective functions are increasing. So that's understandable, technical, and these are understandable. So there are three regions that I have labeled Z1 zones, let's say. Three zones in the space, Z1, Z2, and Z3, as you can see. The idea is that if your problem situation falls into the first zone, Z1, then the way to address this is to use a functionalist approach. You remember we said that there are three approaches: functionalist, interpretive, and emancipatory. So if your problem situation falls into the first zone, we address this situation using a functionalist, from a functionalist point of view. In the second zone, interpretive, and in the third zone, emancipatory. The reason why this is confusing is because the sizes of the volumes are different. As you can see, Z1 occupies a greater volume than Z2, and Z2 than Z3. So if you look at Z3, for example, the technical complexity seems to be reduced from this diagram. I mean, the space occupied by Z3, the values of the technical complexity and the probabilistic complexity in Z3 seems to be less than those in Z1. This is confusing. Don't understand this like this. Now let me try to explain what I mean. Now this figure 1, this is the figure we have seen, shows the three-dimensional space of problem situations. There are three zones, Z1, Z2, and Z3, enclosed by thick gray boundary lines. The relative size of these zones do not indicate the level of complexity of the problem situation. First you have to understand, be careful about this. They do not indicate the level, the sizes do not indicate. For example, a situation that falls into Z3, are you paying attention to this? This is important, okay? Please pay attention to this. You can talk outside. You have all the time. For example, a situation that falls into Z3 can involve a degree of probabilistic complexity as high as that of a situation that falls into Z1. All right? The size of each zone indicates the type of systems thinking that is more suitable for the problem situation of interest. Let me add some more comments on this. In a problem situation that falls in Z3, uncertainty may be as high as a problem situation in Z1. But the volume being smaller, and we are not going as high up in the uncertainty dimension, is because we are not able to handle uncertainty in that situation. In that situation, the conflict of interest is much more powerful than the amount of uncertainty. The complexity introduced by the conflict of interest takes first place, is much more powerful, and this is the first issue that we have to address, rather than the complexity introduced by uncertainty, or the complexity introduced by technical complexities. These are still important, but our approach will give precedence, priority to conflict rather than these. Is this understood? This is what causes confusion. In Z2, for example, if we move from a problem situation in Z3 to another one in Z2, then we will be more able to deal with complexity and technical complexity and uncertainty than we were able in Z3. Now, the complexities are more equally prioritized, we can say. If we move to a problem situation in Z1, then we are more or less not interested at all in purposive complexity because there is a unitary purpose here. All we need to do is to deal with uncertainty and technical complexity. Uncertainty and technical complexity are also present in the other situations, but the priority we accord is to other dimensions of complexity, the conflict, for example. Is this understood? Is this clear? I mean, it's not too difficult to understand. So there are maybe it will be easier to understand all this as we explain the functionalist, the interpreter approaches. So let's take a break.